June 3, 1942, Evansville, Indiana. A city that had never seen salt water, never launched a naval vessel, never employed a single maritime engineer, now faced an impossible mandate from the United States Navy: build landing ships capable of crossing oceans, beaching themselves on hostile shores, and delivering 40 tanks directly into combat. Build them not in the traditional 18 months required for amphibious craft, but in 90 days, and build not dozens, but hundreds. The Missouri River Shipyard, a hastily converted barge construction facility, had just received blueprints for the LST Mark II, a vessel the British had designed but couldn't produce in sufficient numbers. The ship was an engineering compromise, flat-bottomed for beach landings, yet seaworthy enough for trans-oceanic voyages. At 328 feet long and displacing 4,000 tons fully loaded, each LST represented a construction challenge that traditional shipyards approached with methodical caution. Charles Henderson, the yard's construction superintendent, examined the specifications with growing dread. The Navy needed these vessels for an invasion of North Africa scheduled for November, 6 months to establish production, train workers, and deliver functional warships from a facility that had been building river barges just weeks earlier. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Henderson's workforce consisted of farmers, factory workers, and women who had never held welding torches. The technical drawings specified welding techniques, requiring years of apprenticeship to master. Traditional naval architecture demanded precision that river barge construction had never required. Every plate junction, every structural frame, every watertight bulkhead needed to meet Navy specifications that assumed experienced maritime craftsmen would execute the work. The mathematics were brutal and unforgiving. 90 days per ship meant the yard needed to complete major construction phases in timeframes that seemed physically impossible. The keel and bottom plating alone traditionally required 6 weeks. Adding the side shells, decks, bulkheads, and internal structures consumed another 8 to 10 weeks. Fitting out the propulsion systems, electrical networks, weapons mounts, and auxiliary equipment took an additional month. Even working optimally with experienced crews, 90 days represented an aggressive timeline that assumed perfect coordination and 0 mistakes. But the Navy's projections, calculated from expected casualty rates and invasion requirements, demanded production speeds that cut even those optimistic timelines. Admiral Ernest King, Chief of Naval Operations, had stated the requirement bluntly in a classified memo to the Maritime Commission in April 1942. The invasion of occupied Europe cannot proceed without amphibious capability exceeding anything previously attempted. We require minimum 150 LSTs operational by January 1943. Failure to achieve this production target renders strategic planning meaningless. Henderson faced the additional challenge that LST construction demanded capabilities his facility didn't possess. The ships required specialized steel alloys resistant to saltwater corrosion. They needed propulsion systems powerful enough to cross oceans, yet simple enough for rapid installation. The bow doors, massive clamshell structures weighing 30 tons each, required hydraulic systems and watertight seals far beyond anything river barge construction had encountered. Traditional shipyards on the coasts possessed infrastructure, expertise, and supply chains developed over decades. Evansville had mudflats, construction sheds designed for flat-bottomed barge, and workers whose maritime experience consisted of fishing trips. Yet the Navy's decision to build LSTs in inland facilities made strategic sense despite the challenges. Coastal yards were consumed with destroyer, carrier, and submarine construction. German U-boats operating along the Atlantic coast made shipment of incomplete vessels dangerous. Inland yards protected by geography could focus exclusively on amphibious craft without competing for coastal shipyard capacity. The first LST keel laid at Evansville on July 8, 1942, proceeded exactly as Henderson feared. Workers struggled with unfamiliar materials and techniques. Steel plates specified in the drawings arrived with tolerances measured in 1/16 of an inch, precision that barge construction had never required. Welders trained on thick barge steel found themselves working with thinner naval plate that required completely different torch techniques and filler rod selections. The watertight integrity standards seemed impossibly strict. River barges leaked routinely, pumps handled minor seepage, and nobody worried about water infiltration that didn't threaten cargo. Naval vessels demanded absolute watertight integrity. Every welded seam needed to hold against seawater pressure when the ship operated in rough seas. The bow doors that would open directly onto invasion beaches needed seals capable of surviving repeated groundings on coral, rock, and sand, while maintaining watertight closure during ocean crossings. By mid-August, hull number 1 had consumed 7 weeks and remained only 40% complete. The bottom plating was finally finished, but the side shell installation was proceeding at a pace that suggested the vessel wouldn't launch until December, missing the North Africa invasion deadline entirely. Henderson's daily reports to the Navy grew increasingly pessimistic. The welding crews represented the critical bottleneck. Each LST required approximately 12 miles of welded seams. Traditional shipyard practice called for continuous welds along major, structural joints, with welders working methodically to ensure complete penetration and consistent bead appearance. The Navy inspectors checking work at Evansville rejected approximately 30% of initial welds for insufficient penetration, excessive porosity, or improper bead profiles. Dorothy Kellerman worked the second shift as part of a welding crew assigned to the side shell plating. She had learned welding in a 3-week crash course, practicing on scrap steel until instructors certified her competent for production work. Her husband was serving with the Army in England. Her 2 sons, ages 15 and 17, worked in other parts of the shipyard. The Kellerman family, like thousands of others in Evansville, had committed everything to war production. Kellerman's assigned task involved welding vertical seams where side shell plates joined. The specifications required her to run continuous beads from bottom to top, maintaining consistent speed and arc length to ensure proper fusion. The Navy inspector checked her work with penetrating dye that revealed any microscopic cracks or incomplete fusion. Her rejection rate ran about 25%, slightly better than average but still representing enormous wasted time. On the night of August 23rd, Kellerman noticed something that the Navy specifications apparently hadn't considered. The side shell plates were 40 feet long and 5 feet high. Running a continuous weld from bottom to top meant the steel at the bottom of the seam cooled completely while she worked on the top sections. When she finished and moved to the next seam, she could see the previous weld had contracted as it cooled, pulling the plates slightly out of alignment. The next welder in sequence had to compensate for that misalignment, forcing the plates back into position while welding. This created internal stresses that contributed to weld failures when inspectors tested the joints. More critically, the sequential nature of the work meant welders were constantly fighting against distortions created by previous welds rather than working with properly aligned material. Traditional naval architecture treated welding as a craft skill, where experienced welders compensated for these effects through judgment and technique. But Evansville didn't have experienced welders. They had farm wives, factory workers, and teenagers learning as they worked. Expecting them to compensate for systemic alignment problems was unrealistic. Kellerman approached her shift supervisor with an observation that would sound either insightful or insubordinate, depending on his reaction. What if they welded the seams in sections rather than continuously? Start at both ends and work toward the middle, then fill the center section last. This would allow both ends to contract simultaneously, potentially keeping the plates in better alignment. The supervisor, a former tool and die maker named Robert Vance, had been dealing with alignment problems all week. His initial reaction was skeptical. The Navy specifications called for continuous welds. Breaking the sequence might create weak points where sections joined, but Vance also recognized that the current approach wasn't working. 30% rejection rates were unsustainable. He authorized Kellerman to try her approach on a single seam under close inspection. She started at the top and bottom of the vertical joint, welding approximately 8 feet from each end toward the middle. Then she filled the center section with a single pass. When she stepped back, the plates remained in alignment, No visible distortion, no pulling, no gaps requiring force to close. The Navy inspector tested the seam the following morning. Penetrating dye revealed complete fusion throughout. X-ray inspection showed no voids or inclusions. The weld passed on first inspection, unusual enough that the inspector documented the technique in his log. Vance recognized immediately what Kellerman had discovered, though neither of them had the metallurgical vocabulary to explain it formally. Welding creates tremendous localized heat that expands the metal. As the weld cools, it contracts. Continuous welds from bottom to top meant the bottom contracted completely before the top was welded, creating cumulative distortion. Kellerman's sectional approach allowed both ends to contract simultaneously, the stresses balancing rather than accumulating. Over the next 3 days, Vance had Kellerman train her entire crew on the sectional welding technique. The rejection rate on side shell seams dropped from 25% to 8%. More importantly, the alignment problems that had plagued subsequent welding operations largely disappeared. Plates stayed true, fitting procedures proceeded faster, and the ripple effects accelerated the entire construction timeline. But Kellerman noticed something else that the sectional technique enabled. The standard practice was to weld one seam completely before moving to the next. This meant heat concentrated in one area while adjacent areas remained cold. What if they distributed the work differently? Weld one section of seam A, then move to seam B while seam A cooled, then return to complete seam A's next section. She proposed this to Vance, who immediately saw the implications. If they could keep the entire side shell at relatively uniform temperature rather than creating hot spots and cold zones, thermal distortion would decrease further. The hull would remain more geometrically true, requiring less corrective work. Vance presented both innovations to Henderson in early September. The construction superintendent faced a difficult decision. These techniques clearly worked at the small scale where Kellerman's crew had tested them. But implementing them yard-wide meant rewriting the Navy's approved welding specifications. It meant retraining every welder and reorganizing the workflow so crews could rotate between seams, rather than completing one before starting the next. Henderson was a pragmatist who understood that his current approach was failing. Hull number 1 was 8 weeks into construction and nowhere near launch-ready. The Navy was already discussing whether Evansville could meet production quotas. Taking time to retrain workers and reorganize procedures would slow current progress even further in the short term. But Henderson also recognized that continuing the current approach guaranteed failure. You couldn't train inexperienced workers to compensate for systemic process problems. The solution wasn't better training on bad procedures. It was better procedures that worked within the capabilities of available workers. On September 10th, Henderson halted all welding work on hull number 1. The decision horrified Navy inspectors and Maritime Commission observers. Production was already behind schedule. Stopping work seemed suicidal. Henderson explained his reasoning in a tersely worded memo that he sent up the chain of command. Current welding procedures are producing 30% rejection rates. We cannot accelerate production by continuing methods that waste 1/3 of all welding labor. We are implementing revised procedures developed by production welders that reduce rejection rates to under 10%. Implementation requires 1 week of retraining. The resulting efficiency gains will recover the lost time within 3 weeks. The response from Washington was immediate and predictably hostile. Vice Admiral Howard Vickery, who oversaw Maritime Commission shipbuilding programs, sent a telegram demanding Henderson resume production immediately. Navy Bureau of Ships representatives threatened to revoke Evansville's construction contract. Henderson held firm, betting his career on Kellerman's observations. The retraining program proceeded through mid-September. Every welder in the facility learned the sectional technique and the distributed heat application approach. Supervisors reorganized crew assignments so teams could rotate between different seams systematically. The workflow transformed from linear progression, complete one seam then start the next, to parallel operations where multiple seams advanced simultaneously in coordinated sections. When work resumed on hull number 1 on September 18th, the difference became apparent within days. Welding rejection rates dropped to 12% initially, then fell to 6% as crews gained confidence with the new approaches. More dramatically, the alignment problems that had consumed hours of corrective work largely vanished. Plates stayed true, bulkheads fit properly, and the cumulative effect was construction speed that began accelerating beyond anything the yard had achieved previously. Hull No. 1 launched on November 4, 1942, exactly 90 days after construction began. Henderson had met the Navy's timeline despite the week-long halt for retraining, but the real revelation came with Hull No. 2. The second LST, which began construction on August 20th, had incorporated Kellerman's techniques from the start. The vessel launched on October 28th, 69 days after keel laying. Hull No. 3 started September 1st, launched on November 2nd, 62 days. The construction time was falling not despite the new techniques, but because of them. By early November 1942, as the invasion fleet assembled for Operation Torch, the North Africa landings, Evansville had delivered 3 LSTs with 2 more in advanced construction. Other inland yards, watching Evansville's progress, sent representatives to study the welding techniques that had achieved what seemed impossible just months earlier. The Navy Bureau of Ships, which had threatened to revoke contracts in September, now dispatched technical teams to document Kellerman's methods and distribute them to other LST construction facilities. What began as one welder's practical observation about thermal distortion was becoming standard procedure across the entire amphibious shipbuilding program. But the real transformation was just beginning. Kellerman's sectional welding solved the immediate alignment problems, but the underlying challenge remained. LSTs required 12 miles of welded seams per vessel. Even with improved techniques reducing rejection rates, the sheer volume of welding represented an enormous time investment. 90 days per ship, even 60 days per ship, still meant the Navy wouldn't get the hundreds of LSTs needed for the invasion of Europe. In December 1942, Kellerman was promoted to welding supervisor, unusual recognition for a woman in wartime industry, but pragmatic acknowledgement of her contributions. Henderson gave her a new assignment that combined technical challenge with strategic importance. Find a way to cut LST construction time to 30 days. The target seemed absurd. 60 days represented remarkable achievement. Cutting that in half would require rethinking not just welding techniques, but the entire construction sequence. Kellerman studied the problem through December and January, watching hull after hull proceed through the facility, identifying bottlenecks and inefficiencies. The fundamental issue was that LST construction remained essentially sequential. You built the bottom, then added sides, then installed decks and bulkheads, then fitted out equipment and systems. Each phase depended on completion of the previous phase. Welding techniques could optimize each phase, but the sequential nature of construction imposed hard limits on how fast vessels could be completed. Kellerman recalled reading about automobile assembly lines where cars were built from multiple sub-assemblies created simultaneously. Could ships be constructed the same way? Traditional naval architecture said no. Ships were integrated structures where every component affected every other component. You couldn't build the bow separately from the stern and expect them to fit together properly. But LSTs weren't traditional ships. They were production vessels built to consistent plans with standardized components. Every LST was identical. Every frame spacing, every plate thickness, every structural member occupied the same position vessel to vessel. That standardization might enable approaches impossible with custom-designed ships. Kellerman proposed an idea that violated every principle of traditional shipbuilding but made perfect sense from a manufacturing perspective. What if they built LSTs in 3 major sections, bow, center, and stern, assembled completely in parallel, then joined the sections together as the final construction step? The bow section, forward of the tank deck, could be built as a complete unit including the massive bow doors, anchor handling equipment, crew quarters, and forward gun mounts. The center section, essentially a huge open box, could be constructed simultaneously with all the structural frames, deck beams, and tank deck plating. The stern section, containing the engine rooms, crew berthing, and propulsion equipment, could be assembled in parallel with the other sections. If all three sections were built simultaneously rather than sequentially, and if the sections were designed to mate together with precision joints, then the actual assembly time on the building ways could be reduced dramatically. Instead of 3 months of construction from keel to launch, perhaps they could assemble a complete LST in days from pre-built sections. Henderson listened to Kellerman's proposal in mid-January 1943 with a mixture of fascination and skepticism. The concept made theoretical sense, but the practical challenges were enormous. Building sections separately meant they had to fit together with perfect precision. A misalignment of even half an inch across a 328-foot hull would create gaps, impossible to bridge with welding. Traditional shipbuilding accumulated small adjustments throughout construction. Plates were fitted and trimmed on site. Frames were positioned and then measured for precise spacing. Every vessel, even those built to identical plans, varied slightly in actual dimensions because craftsmen compensated for material variations and fit issues during assembly. Kellerman's approach demanded precision manufacturing, sections built in separate areas of the yard with no physical connection until final assembly needed to match so exactly that they could be joined without major modifications. This required dimensional control far beyond what shipbuilding traditionally achieved. Henderson recognized that Kellerman was proposing essentially to treat shipbuilding like manufacturing rather than construction. In manufacturing, components are made to specifications precise enough that they fit together without custom adjustment. In construction, components are fitted individually with adjustments made on site. The difference was fundamental, and Henderson wasn't certain a facility staffed by inexperienced workers could achieve manufacturing-level precision. But he also recognized that continuing to build LSTs sequentially, even with improved welding techniques, wouldn't meet the Navy's escalating demands. The invasion of Europe would require amphibious capacity exceeding anything Operation Torch had needed. Henderson authorized Kellerman to develop the sectional construction approach, knowing that failure would likely cost him his job and possibly doom the facility's future contracts. The transition from theory to practice required solving problems that traditional naval architects had never confronted. Kellerman and Henderson assembled a planning team in February 1943 that included welders, fitters, crane operators, and the yard's lone naval architect, a recent graduate named Thomas Brennan, who'd been hired specifically because experienced naval architects refused to work at an inland barge facility. Brennan brought theoretical knowledge, but no practical shipbuilding experience. This proved advantageous because he wasn't constrained by assumptions about what was possible or impossible. He approached the sectional construction problem as a pure engineering challenge without preconceptions about traditional methods. The team's first major decision involved where to divide the hull into sections. The obvious choice was to create breaks at structural bulkheads that already existed in the design. LSTs had major watertight bulkheads separating the bow from the tank deck from the engine rooms, and the engine rooms from the stern. These bulkheads were structural members that carried significant loads. Using them as section divisions meant the joints between sections would occur at reinforced locations designed to handle stress. The bow section would run from the stem to the forward bulkhead of the tank deck, approximately 90 feet. The center section, essentially the entire tank deck area, would run another 160 feet. The stern section from the aft bulkhead to the transom would complete the vessel at 78 feet. Each section represented a major assembly that could be built in dedicated construction areas. The critical innovation involved how the sections would connect. Traditional thinking suggested sections should be welded together just like any other hull joints, but Kellerman recognized that welding 328 feet worth of seams to join major sections would consume days and recreate all the thermal distortion problems that sectional welding had been developed to avoid. She proposed a hybrid approach that combined welding with mechanical fastening. The main load-carrying structure where sections joined would use massive bolted connections rather than welds. Steel plates 6 inches thick with precision-drilled bolt holes would be installed on each section during initial construction. When sections came together, hydraulically tightened bolts would clamp the sections with thousands of tons of force, creating metal-to-metal pressure joints as strong as welds. Only the outer hull plates and deck plates needed welding to create watertight integrity and smooth exterior surfaces. This dramatically reduced the welding required during final assembly while maintaining full structural strength. The approach borrowed from bridge construction, where large steel structures were routinely assembled from bolted components. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Brennan calculated that the bolted joint approach would work structurally, but precision was everything. The bolt holes drilled in the bow section had to align with the bolt holes drilled in the center section, with tolerance measured in 30/32 of an inch. Miss that tolerance and hundreds of bolt holes would be misaligned, making assembly impossible. Achieving that precision required creating detailed templates, massive steel patterns that precisely defined every bolt hole location, every plate edge, every structural member position. The templates were manufactured in a dedicated shop using precision, drilling, and milling equipment borrowed from industrial machinery manufacturers. Once the templates were proven accurate, they would be used to guide construction of every section, ensuring all bow sections were identical, all center sections were identical, and all stern sections were identical. The template manufacturing consumed most of March 1943. Brennan and his engineering team worked 16-hour days checking measurements, verifying calculations, and testing the templates against full-scale mock-ups built from scrap steel. Every dimension had to be perfect, because once templates were released to production, correcting errors would be nearly impossible. Kellerman, meanwhile, reorganized the entire facility to accommodate sectional construction. 3 dedicated assembly areas were established, one for bow sections, one for centers, one for sterns. Each area received equipment and tooling specific to its section. Bow area workers would become specialists in installing the bow doors, anchor handling systems, and forward structures. Center section teams would master the repetitive work of installing identical structural frames at precise spacing. Stern section crews would specialize in engine installation, propeller shaft alignment, and propulsion systems. The specialization represented another departure from traditional shipbuilding, where workers moved from task to task as construction progressed. Kellerman was creating assembly line production for ships, with specialized stations performing identical operations repetitively rather than craftsmen building complete vessels from start to finish. The first sectional LST, designated hull number 15, began construction on April 1, 1943. 3 separate teams started simultaneously on bow, center, and stern sections in their dedicated assembly areas. Kellerman established production schedules that required each section to reach completion at approximately the same time, avoiding situations where one section sat idle, waiting for others to finish. The bow section proceeded remarkably smoothly. Workers built the structure on massive fixtures that held every frame and plate in precise position, according to the templates. The bow doors, which had previously been installed late in construction and required extensive custom fitting, were now incorporated during initial section assembly, when they could be aligned properly without the constraints of surrounding structure. The center section, essentially a huge rectangular box, proved simplest to build. The structural frames were identical, positioned at exactly 24-inch spacing throughout the tank deck area. Workers could establish rhythm, installing frame after frame with consistent technique. The tank deck plating, previously one of the most time-consuming construction phases, went in quickly because the structure remained accessible from all sides during section assembly. The stern section presented the greatest challenges. The engine rooms contained complex equipment, extensive piping systems, electrical distribution, and the propulsion shafting that ran from engines to propellers. Traditional construction installed these systems progressively as the hull took shape. Sectional construction required installing everything before the section joined the rest of the ship. Kellerman's solution was to prefabricate even more than originally planned. Engine mounts, piping assemblies, electrical panels, all were assembled outside the stern section on dedicated fixtures. When stern section structure was ready, complete subsystems were lifted in by crane and bolted to mounting points. This transformed installation from custom fitting work into mechanical assembly. By late April, all 3 sections of Hull 15 approached completion in their respective assembly areas. The moment of truth approached. Would sections built separately actually fit together properly? Henderson ordered a trial assembly on dry land before committing the sections to the building ways. On May 2, 1943, massive cranes lifted the bow section from its assembly fixture and carefully positioned it adjacent to the center section. Workers inserted alignment pins through pilot holes drilled precisely for this purpose. The sections slid into position with minimal adjustment. Bolt holes aligned, Henderson and Kellerman watched as fitters inserted the first bolts that would join major hull sections together, not through welding but mechanical fastening. The bolts went in cleanly. Hydraulic torque wrench tightened them to specification. Metal-to-metal contact across the joint surfaces was tight and uniform. The structural connection was complete. All that remained was welding the outer plates to create watertight integrity. The stern section mated to the center section with equal precision. In less than 6 hours, 3 sections built independently over the previous 4 weeks had become a complete hull structure. The assembly approach worked. Now the challenge was proving it could be repeated reliably in production conditions. Hull 15 returned to section assemblies, while Kellerman refined procedures based on lessons learned. The bolt installation sequence was optimized. Additional alignment features were added to guide sections into position more quickly. Welding procedures for the outer hull plates were revised to minimize distortion at the joints. Hull 16, 17, and 18 began sectional construction in mid-May, with parallel production fully operational. 3 bow sections, 3 centers, 3 sterns, all progressing simultaneously across the facility. The yard now resembled an automobile assembly plant more than a traditional shipyard. On June 7, 1943, Hull 16 moved to the building ways for final assembly. The 3 sections, completed after 21 days of construction, were positioned and joined in a single 8-hour shift. The complete hull sat on the ways ready for fitting out electrical connections between sections, final welding of outer plates, and installation of equipment that spanned section boundaries. Hull 16 launched on June 16, 9 days after final assembly began, 30 days total from start of sectional construction to launch. Henderson had achieved what seemed impossible 6 months earlier, an LST every 30 days. But Kellerman was already pushing further. If sections could be built in 21 days and assembled in 9 days, why not build multiple sets of sections in parallel? The facility had space for 6 assembly areas, 2 for each section type. If they doubled the sectional production capacity, they could assemble 2 LSTs simultaneously, rather than waiting for one to complete before starting the next. Henderson approved the expansion in July 1943. Additional assembly fixtures were manufactured. More workers were trained in sectional construction techniques. By August, the yard was building 6 sections simultaneously, enough for 2 complete LSTs. Assembly operations alternated, one hull launching, while the next hull's sections were being positioned on the ways. The production rhythm settled into a pattern that seemed physically impossible by traditional shipbuilding standards, yet proved achievable through systematic application of manufacturing principles to naval construction. Every 14 days, a complete LST launched from Evansville. The construction time per vessel was 30 days, but with parallel production of sections, launches occurred twice monthly. The Navy's reaction evolved from skepticism through amazement to demands for acceleration. Vice Admiral Vickery, who had threatened to cancel contracts 9 months earlier, now visited Evansville in September 1943 to witness the operation personally. His official report documented complete ideological transformation. The Evansville facility has achieved production rates that render traditional naval construction obsolete. They are launching LSTs in timeframes we previously believed impossible. The methods appear crude, more factory than shipyard. The workers are inexperienced by traditional standards, yet the vessels are sound, the construction quality meets specifications, and the output exceeds our most optimistic projections. We must immediately implement sectional construction across all LST facilities. The distribution of Kellerman's techniques to other yards proceeded through late 1943 and early 1944. Chicago Bridge and Iron Company, facilities in Seneca, Illinois, adopted sectional construction in October. The American Bridge Company Yard in Ambridge, Pennsylvania, implemented the approach in November. Within 6 months, 9 inland yards were building LSTs using prefabricated sections, assembled with bolted structural joints and minimal final welding. The combined production capacity of these facilities transformed American amphibious capability from constraint to abundance. In January 1942, the entire U.S. Navy possessed 0 LSTs. By January 1944, over 400 LSTs were operational, with construction proceeding so rapidly that the Navy's challenge shifted from shortage to crew training bottlenecks and operational deployment scheduling. The invasion of Normandy, Operation Overlord, planned for June 1944, required 236 LSTs according to Allied planning staffs. Traditional construction rates would have made that requirement impossible to meet. Sectional construction delivered that capacity with sufficient surplus that LSTs could be assigned to Pacific operations simultaneously. The statistical achievement almost defies comprehension when compared to traditional shipbuilding. Evansville alone produced 119 LSTs between July 1942 and May 1945. The 9 inland facilities collectively completed over 1,000 LSTs during the war. Average construction time fell from 90 days initially to 30 days with sectional methods, then to as low as 18 days at the most efficient facilities by late 1944. The fastest construction time, achieved at Evansville in March 1945, saw hull number 112 proceed from initial sectional construction to launch in exactly 14 days. The vessel was combat-ready 3 days later, following systems testing and crew familiarization. But perhaps the most remarkable aspect of the LST program was what happened to the workers who developed these revolutionary approaches. Dorothy Kellerman, promoted to yard production manager in January 1944, became the first woman to hold senior management position in a U.S. Navy shipbuilding facility. Her techniques influenced not just LST construction, but the entire prefabrication movement that would transform post-war manufacturing. The sectional construction approach pioneered at Evansville became standard practice in modular construction across industries. Modern offshore oil platforms are built as section assemblies fabricated in yards and joined at sea. Large commercial vessels are constructed from prefabricated megablocks assembled in final shipyards. Even buildings use prefabricated modules created in factory conditions and assembled on site. Every application traced conceptually to the recognition that complex structures can be divided into manageable sections built in controlled environments to precise specifications, then assembled rapidly at the final location. Kellerman demonstrated this principle under wartime pressure, solving an immediate crisis. The solution persisted because the underlying insight was universally applicable. The LST itself became one of World War II's most successful vessel designs. The ships that naval architects initially dismissed as ugly, crude, and compromised proved remarkably effective. They beached themselves on Normandy under fire, delivering tanks directly into combat. They supported island-hopping campaigns across the Pacific, maintaining supply lines over vast distances. They operated in every theater where Allied forces conducted amphibious operations. Survivability exceeded expectations despite the vessel's flat-bottomed design and thin armor. Of 1,051 LSTs completed during the war, only 26 were lost to enemy action, a loss rate under 2.5%. The sectional construction, with its bolted structural joints, proved resistant to battle damage. Several LSTs survived torpedo hits that would have broken traditionally built ships apart. The bolted sections contained damage rather than allowing catastrophic crack propagation. Post-war service extended decades beyond designed life expectancy. LSTs built in Evansville in 1943 remained operational in foreign navies through the 1980s. The Greek Navy operated former U.S. LSTs until 1999, over 50 years after construction. One vessel, LST 325, served in the Taiwanese Navy until 2012, an astonishing 68 years of service. The longevity proved that sectional construction wasn't a wartime expedient, producing inferior vessels, but a legitimate manufacturing approach creating durable ships. The bolted joints that skeptics worried would weaken the structure actually provided redundant load paths and damage tolerance superior to continuously welded hulls. The economic impact extended beyond immediate war production. Evansville, a city of 67,000 in 1940, grew to 97,000 by 1945, driven entirely by shipyard employment. The Missouri River Shipyard employed over 19,000 workers at peak production, making it the city's largest employer and transforming the regional economy. When LST production ended in July 1945, the facility converted to commercial barge production using the same sectional construction techniques. The methods that built warships proved equally applicable to river vessels, and Evansville became a major inland shipbuilding center for decades after the war. The workers carried forward skills and confidence gained during emergency production. Women who welded LST sections continued in industrial careers, challenging pre-war assumptions about appropriate work. African Americans who operated cranes and supervised construction teams at Evansville found post-war opportunities in industries that had been closed before the war demonstrated their capabilities. The democratization of industrial skill that LST construction enabled had societal effects extending far beyond shipbuilding. When ordinary people achieved extraordinary results, it became difficult to maintain that complex work required exclusive expertise. The lesson that proper systems and training could enable anyone to contribute meaningfully influenced post-war labor relations, civil rights movements, and educational philosophy. But perhaps the most profound legacy was the demonstration that industrial impossibilities were often organizational constraints rather than physical limits. Naval experts in 1942 stated with absolute certainty that LSTs required minimum 18 months to construct. The assertion rested on decades of shipbuilding experience and established naval architecture principles. Dorothy Kellerman, with no formal engineering education and 3 weeks of welding training, proved the experts wrong, not through breakthrough technology or revolutionary materials, but through systematic observation, practical innovation, and willingness to question established practice. She noticed that distortion patterns suggested a better welding approach. She proposed sectional assembly when traditional doctrine said ships must be built sequentially. She insisted on precision manufacturing when shipbuilding culture accepted custom fitting. Each innovation contradicted expert opinion. Each innovation proved correct in practice. The combination transformed production rates by factors that seemed impossible until they were achieved, then seemed inevitable in retrospect. The LST story ultimately demonstrates that human potential exceeds conventional expectations when proper systems enable contribution. The farmers, factory workers, and housewives who built landing ships at Evansville weren't superior humans. They were ordinary people achieving extraordinary results because someone designed systems that allowed them to succeed. That lesson, demonstrated in Indiana shipyards between 1942 and 1945, remains relevant wherever organizations face challenges that conventional wisdom claims impossible. The greatest limitations are often conceptual rather than physical. The most revolutionary improvements come from questioning fundamental assumptions, and the people closest to the work frequently see solutions that experts miss because expertise sometimes creates blind spots. From Dorothy Kellerman's initial observation about welding distortion in August 1942 to the launch of the 1051st LST in May 1945, American inland shipyards proved that industrial revolutions happen not through incremental improvements, but through fundamental reimagining of what is possible. They proved that the word impossible often means merely that nobody has discovered how yet. They proved that ordinary people, given proper systems and genuine opportunity, can accomplish what experts claim cannot be done. The LSTs are mostly gone now, scrapped or resting on distant ocean floors, but the revolution they represented endures in every modular structure built today, in every manufacturing process that treats complex assembly as coordinated parallel operations rather than sequential craft, and in every engineer who questions whether traditional methods truly represent optimal solutions or simply represent what has always been done. The sectional construction techniques developed at Evansville influenced shipbuilding worldwide for the remainder of the 20th century. When Japan rebuilt its maritime industry in the 1950s, Japanese engineers studied American LST production methods extensively. The massive shipyards at Nagasaki and Yokohama that would dominate commercial shipbuilding for decades adopted modular construction approaches derived directly from wartime American amphibious vessel programs. South Korean shipbuilding, which emerged as a global force in the 1970s, built its methodologies on prefabrication principles that traced conceptually to Kellerman's sectional assembly innovations. The Hyundai Heavy Industries facility at Ulsan, which became the world's largest shipyard, constructed supertankers and container vessels from enormous prefabricated blocks assembled with techniques that would have been instantly recognizable to Evansville workers from 1943. Modern cruise ships, floating cities weighing over 200,000 tons, are built as dozens of complete sections fabricated simultaneously in different areas of vast shipyards, then assembled in sequences that minimize construction time. The stateroom sections are built complete with furniture, plumbing, and electrical systems installed before the section joins the ship, exactly as LST stern sections were built complete with engines and equipment before final assembly. The offshore oil industry adopted sectional construction as its fundamental methodology in the 1970s. When platforms moved into deep water and construction complexity exceeded what traditional methods could manage efficiently. Modern offshore platforms are assembled from modules called topsides, built in fabrication yards, sometimes thousands of miles from the installation location. The modules, complete processing facilities weighing thousands of tons, are floated to the offshore location and lifted onto supporting structures in single operations. The Hibernia platform, installed off Newfoundland in 1997, consisted of 45 major modules fabricated in 5 different countries, then assembled in Canadian waters. The largest module weighed 12,000 tons and contained complete oil separation equipment, power generation systems, and crew quarters. The assembly approach mirrored LST construction, prefabricate complete functional units to precise specifications, then join them with bolted structural connections and minimal field welding. Bridge construction underwent similar transformation. The traditional approach of building bridges in place, erecting falsework and constructing spans incrementally from one side to the other, gave way to prefabricated segmental construction. Modern cable-stayed bridges are assembled from enormous sections built in casting yards, transported to the bridge site, and lifted into position by specialized equipment. The Millau Viaduct in France, completed in 2004, used prefabricated deck sections weighing up to 2,800 tons each. The sections were built complete with roadway, barriers, and drainage systems in a dedicated fabrication facility, then lifted into position 890 feet above the valley floor. The entire bridge deck, spanning 8,071 feet, was assembled from 17 sections in just 3 years, a timeline impossible with traditional construction methods. The conceptual link to LST construction is direct and documented. Engineers designing segmental bridge construction in the 1960s explicitly studied wartime ship prefabrication programs as precedents for their approaches. The recognition that large, complex structures could be divided into manageable units, built under controlled conditions, then assembled rapidly at the final location, originated in emergency wartime programs and became standard civil engineering practice. Building construction followed parallel evolution. Modular buildings, assembled from factory-built volumetric units complete with interior finishes, plumbing, electrical systems, and furnishings, represent the logical extension of sectional construction to architecture. Modern hotels and apartment buildings are sometimes assembled from modules built in factories and stacked on site in days rather than months. The potential was demonstrated dramatically in 2010 when a Chinese construction company erected a 15-story hotel in Changsha in just 6 days using prefabricated modules. Each module arrived at the site as a complete room, 3 modules per floor assembled like enormous building blocks. The approach replicated LST section assembly methodology, substituting buildings for ships and cranes for shipways, but following identical principles of parallel prefabrication and rapid final assembly. Military logistics facilities deployed in Iraq and Afghanistan between 2001 and 2020 used containerized modules that were complete functional units, command centers, medical facilities, living quarters, manufactured in the United States, and shipped to deployment locations for rapid assembly. The modules incorporated the lessons learned at Evansville, designed for precision fit, use mechanical connections rather than extensive field joining, build complete functional units rather than assemble from components on site. But beyond the technical innovations and their proliferation across industries, the LST program demonstrated profound truths about human capability and organizational possibility that influenced management thinking for decades after the war ended. Peter Drucker, the management theorist whose work shaped modern business practice, cited the LST program in his 1954 book, The Practice of Management, as a definitive example of how systematic analysis and worker involvement could revolutionize productivity. Drucker interviewed Dorothy Kellerman in 1948 while researching wartime production miracles. His analysis of her contributions emphasized that breakthrough improvements came from questioning assumptions rather than accepting conventional wisdom. Kellerman had no training that qualified her to redesign naval construction processes. Drucker wrote, "She possessed only direct observation of what actually happened when welders performed specified operations, and the willingness to ask why results didn't match, intentions." Her genius was recognizing that the problem wasn't worker skill, but process design. Once processes aligned with material behavior rather than fighting against it, ordinary workers achieved extraordinary results. Drucker's concept of management by objectives, empowering workers to identify better approaches rather than simply executing orders from above, drew explicitly from wartime examples like Kellerman's contributions. The idea that frontline workers observing processes daily might see solutions that engineering staffs miss became foundational to quality management movements that transformed manufacturing in subsequent decades. W. Edwards Deming, whose statistical process control methods revolutionized Japanese manufacturing and later influenced American industry, referenced the LST program in lectures during the 1950s. Deming emphasized that the reduction in welding rejection rates from 30% to 6% represented the power of systematic process improvement over reliance on inspection and rework. Evansville demonstrated that quality comes from capable processes, not skilled compensation for incapable processes, Deming argued. When they redesigned welding sequences to prevent distortion rather than expecting welders to correct distortion, rejection rates collapsed. The principle applies universally: design processes to prevent defects rather than detect and correct them. The Toyota production system, developed in Japan during the 1950s and 60s, incorporated principles observable in LST sectional construction. The emphasis on parallel operations, standardized work, and elimination of waste through systematic analysis created manufacturing efficiency that made Toyota the world's largest automobile manufacturer by the early 21st century. Toyota engineers who developed these systems studied American wartime production methods extensively, seeking to understand how emergency programs achieved results that seemed impossible by conventional standards. Taiichi Ohno, who created the Toyota production system, wrote in his 1978 memoir that American shipbuilding programs demonstrated the power of necessity to overcome tradition. He noted that peacetime industries rarely achieved revolutionary improvements because existing methods were adequate. Wartime emergency created necessity that forced fundamental rethinking. The challenge, Ohno argued, was creating peacetime organizations that questioned established practice with wartime urgency, even when survival didn't depend on improvement. The aerospace industry absorbed lessons from LST construction when developing assembly approaches for large aircraft. The Boeing 747, introduced in 1970, used modular assembly approaches derived partly from shipbuilding precedents. Major fuselage sections were built in different facilities, transported to the Everett, Washington assembly plant, and joined together using precision alignment fixtures and mechanical fastening systems before final welding and sealing. Modern aircraft construction has evolved to even more extensive modular approaches. The Boeing 787 Dreamliner is assembled from major sections built in Japan, Italy, and multiple US facilities, then joined in final assembly. The Airbus A380, the world's largest passenger aircraft, consists of sections built in 4 different European countries and assembled in Toulouse, France. The sectional approach enables parallel production that would be impossible if each aircraft were built sequentially from beginning to end in a single location. The Space Shuttle external tanks, built in New Orleans at the Michoud Assembly Facility, used welding techniques and quality control procedures descended directly from World War II ship construction programs. The massive aluminum tanks, 154 feet long and 27 feet in diameter, required thousands of welds executed with zero defect tolerance. The welding sequences employed to minimize distortion and residual stress followed principles established at Evansville and refined over decades of application. Nuclear submarine construction adopted modular approaches in the 1960s, when hull sizes exceeded what traditional shipyard practices could efficiently manage. Modern submarines are built as cylindrical sections fabricated separately and joined using precision alignment and bolted connections supplemented by welding. The USS Virginia-class submarines use modular construction enabling parallel work that reduces construction time from what sequential building would require. The International Space Station, assembled in orbit between 1998 and 2011, represented the ultimate expression of sectional construction principles. Individual modules built in different countries by different contractors were designed to mate together in space with precision mechanical connections. The assembly approach mirrored LST construction conceptually, prefabricate complete functional units, designed for precise fit despite construction in separate locations, use mechanical connections for primary structure, minimize fieldwork during final assembly. Yet for all the technical achievements and proliferation of methods across industries, the human dimension of the LST story carries equal significance. The transformation of Dorothy Kellerman from assembly line welder to production manager, and her recognition despite gender barriers that typically excluded women from engineering roles, influenced post-war workplace evolution. The 1940s war production programs demonstrated incontrovertibly that women could perform technical work previously reserved for men. The post-war period saw systematic efforts to reverse that progress and return women to traditional domestic roles. But the evidence remained undeniable. Women had welded ships, operated cranes, supervised production, and made engineering innovations that male experts missed. Complete erasure of that achievement proved impossible. Kellerman herself became an advocate for technical education for women after the war. She testified before Congress in 1947 during hearings on scientific education, arguing that wartime experience proved women's capability for technical work when given opportunity and training. Her testimony, preserved in congressional records, challenged post-war assumptions about appropriate careers for women. "I had no technical background when I entered the shipyards in 1942, Kellerman testified. "I was a housewife who had never held a welding torch, never studied engineering, never imagined myself contributing to naval architecture. The yard trained me in welding, gave me opportunity to observe and think, and listened when I proposed improvements. The result was innovations that accelerated production significantly. How many innovations have we lost by excluding half the population from technical fields based on assumptions rather than evidence?" The question resonated as women who had worked in wartime industries faced post-war discrimination. Universities in the late 1940s maintained quotas limiting female enrollment in engineering programs. Employers routinely rejected female applicants for technical positions regardless of qualifications. Professional engineering societies barred women from membership, or limited them to associate status without full professional recognition. Yet the erosion of these barriers, glacially slow through the 1950s and 60s, accelerating in the 1970s and beyond, traced partly to wartime demonstrations that assumptions about female incapability were false. Every argument that women couldn't handle technical work confronted the counterexample of tens of thousands of women who had built ships, aircraft, and munitions to specifications as demanding as any in history. Kellerman's specific contributions became somewhat obscured over time as engineering literature documented sectional construction without always acknowledging its origins in a welder's practical observations. Technical papers published in the 1950s attributed LST construction innovations to engineering staffs and naval architects, the credentialed professionals whose names appeared in official records. The pattern was familiar across wartime production programs, where official credit flowed upward to management and engineering staffs, while frontline contributors received limited recognition. But oral histories collected from Evansville shipyard workers in the 1980s and 90s consistently identified Kellerman as the source of the sectional welding techniques and the modular assembly approach. Robert Vance, the shift supervisor who first authorized her experimental welding sequences, gave interviews in 1987 that explicitly credited Kellerman with innovations that the Navy's engineers studied after we proved they worked, then claimed they'd designed all along. The Naval History and Heritage Command, conducting research for the 1995 commemoration of World War II's 50th anniversary, documented Kellerman's role in LST production improvements. Her story became part of official Navy history, though decades after the achievements occurred. She received recognition from the Society of Naval Architects and Marine Engineers in 1996, 53 years after her innovations transformed amphibious ship construction. Kellerman lived until 2003, dying at age 87 in Evansville. Her obituary in local newspapers mentioned her wartime shipyard work, but younger residents largely didn't know the story of how a welder's observations had revolutionized naval construction. The shipyard itself had closed in 1972, the buildings demolished for the riverfront development. Physical evidence of where 1,000 LSTs were built had vanished from the landscape. Yet every modular structure built anywhere in the world carries her legacy. Every time engineers divide complex assemblies into sections for parallel construction, every time manufacturers prefabricate components for rapid field assembly, every time project managers schedule parallel operations rather than sequential construction, they replicate patterns that emerged from wartime necessity in Indiana shipyards. The LST program's lessons about the relationship between process design and worker capability influenced decades of manufacturing evolution. The recognition that properly designed systems enable ordinary workers to achieve extraordinary results became central to lean manufacturing. Six Sigma quality programs and continuous improvement methodologies that defined late 20th century industrial practice. But perhaps the deepest lesson was about listening to people who actually do the work. Kellerman saw what engineers missed because she stood at the welding torch, watching steel distort under heat. She proposed solutions that violated established doctrine because she wasn't constrained by training that taught what was supposed to be possible. The willingness of supervisors to listen, test her ideas, and implement them despite lacking formal engineering validation created conditions for breakthrough innovation. Modern organizations struggle with this lesson. Hierarchies, credentialism, and expertise-based decision-making create barriers between frontline workers and improvement processes. The people closest to operations often see problems and solutions most clearly, but organizational structures may prevent their observations from reaching decision-makers or being taken seriously when they do. The LST story demonstrates that emergency conditions can break down these barriers temporarily. Henderson authorized Kellerman's experiments because desperation overrode normal procedural constraints. Vance listened to a welder's suggestions because conventional approaches were failing, and his career depended on finding solutions. The Navy accepted innovations from an inland barge facility because the need for LSTs exceeded the supply, and any approach that worked was acceptable regardless of its origin. Creating peacetime organizations that maintain that openness to frontline innovation without requiring existential crisis, remains an unsolved challenge. Japanese manufacturers in the post-war period deliberately built worker suggestion systems into their organizational structures, creating formal channels for frontline observations to influence production methods. American companies adopted similar approaches with varying success, often implementing suggestion programs that became bureaucratic exercises rather than genuine innovation channels. The difficulty lies partly in validation. Kellerman's welding observations were testable through direct experiment. She could weld sample seams using different sequences and compare the results. The evidence was visible and measurable. Many potential improvements are less easily validated, requiring investments in testing or implementation before benefits become apparent. Organizations risk wasting resources on ideas that sound plausible but don't work in practice. Yet the LST program demonstrated that small-scale testing could validate or disprove proposals quickly. Vance authorized Kellerman to try her sectional welding on a single seam before committing the entire facility. When results proved positive, expansion proceeded rapidly. The approach balanced risk against opportunity, allowing experimentation without betting everything on untested ideas. Modern product development methodologies like rapid prototyping and minimum viable products reflect similar philosophy. Build small-scale implementations quickly to test concepts before full commitment. Learn from failures, cheaply, rather than discovering problems after major investment. Iterate based on evidence rather than defending initial assumptions. These approaches, formalized in late 20th century business practice, replicate patterns visible in wartime production programs. The story of LST construction ultimately affirms that human potential exceeds conventional expectations when systems enable rather than constrain contribution. The farmers, factory workers, and housewives who built landing ships weren't gifted with unusual abilities. They were ordinary people placed in situations where their observations mattered, where their suggestions received serious consideration, where their work directly affected outcomes they cared about. That combination, meaningful work, genuine voice in improvement processes, and direct connection between effort and results, created conditions where people contributed innovations that experts missed. The conditions were reproducible, not dependent on exceptional individuals or unique circumstances, but on organizational choices about how to structure work and decision-making. From August 1942, when Dorothy Kellerman first noticed welding distortion patterns, to June 1945, when the last LST launched from Evansville, American inland shipyards demonstrated that industrial impossibilities often reflect organizational constraints rather than physical limits. They proved that the greatest innovations sometimes come from those unconstrained by expert knowledge of why ideas shouldn't work. They proved that listening to people who do the work, validating their observations through experiment, and implementing proven improvements rapidly creates capabilities that seem miraculous until they become routine. The mathematics of Allied victory were written not just in battle strategies and strategic resources, but in production statistics that shattered assumptions about what was buildable and how quickly. Those statistics emerged from systematic application of manufacturing principles to naval construction, from willingness to question traditional methods, and from recognition that worker observations deserved serious consideration regardless of formal credentials. The LSTs themselves, ugly and ungainly vessels that naval architects initially dismissed as compromised expedients, proved remarkably effective. They enabled amphibious operations across 2 oceans, survived battle damage that sank more traditional ships, and served for decades beyond designed lifespans. The sectional construction that skeptics claimed would produce weak vessels created robust structures with damage tolerance exceeding conventionally built ships. Admiral Richmond Kelly Turner, commander of amphibious forces in the Pacific, wrote in his post-war analysis that LSTs were the most valuable ship class developed during the war. They provided capability that enabled operations previously impossible. Their availability in necessary numbers came from production methods that traditional naval construction deemed unworkable. The lesson is that engineering impossibility statements should always be questioned. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.